in length at the very least to be able to unify, or it will fail. And if the values are different at any point in the list, then unification will fail. The way to do that is we unify the heads, and we take the result of that, and we unify the tails. So we will recurse through the list until it's empty, essentially, or until we hit a snag. And speaking of snags, first, the base case. If u equals v, assuming at this point that both u and v will be valued because we've tested for variables already, then just return s unchanged. You can say 1 equals 1, and that's fine. We don't need to record that fact. However, if none of these succeed, I use the underscore to match anything. At this point, I don't care what u and v are, because I know that that means we are failing. So I return nil. And that's the end of my match. So let's test that. So how should I do this? Didn't I have a... Oh, essentially, I could go... I could try assigning a logic variable. Let's say that I want to define a relation that logic variable 0 is 1337. And pass an empty dictionary. That's the state. So this isn't entirely readable, but you can see over here, essentially, this is the binding. Logic variable 0 is 1337. So it's decided that unification succeeded, and we have a new binding.
So the minus 57 is just the name of one state?
It's, I'm guessing it's some implementation data, perhaps the hash of the key or something. Because this is a hash dictionary.
But it's not important in any way.
It's not important. That is just how Pure chooses for some reason to output the dictionary. The important bit is only this, essentially.
There's only one solution for the goal.
That would essentially be, well, not the goal, we're not at goals yet, but that will be the result of the unification.
Okay.
That we now know that logic variable 0 is plus 100. Yeah. We're guessing that in just a second. Don't worry. Just want to show you that it can succeed with no values being found, if indeed we pass in two more values, and if we pass in different values.
Is that photo?
What?
Is nil? What nil was? There's no satisfying state.
Oh, this is. Let me show you.
A dictionary.
Yes, this is empty h date.
All right.
Did I describe it? I don't know why I did that. Empty h date. Yeah, there we go. That's the empty dictionary, essentially. It is literally the same thing, isn't it? That's because I terminated the line above. Right, so where were we? I'm going to try and make that fail. So if we say that 1337 equals 4489, is that nil? No, it doesn't. You can't. So that will be a failed unification. Now, we happen to have everything we need to produce the first goal operator. And I'm going to adopt a syntax like something like u question mark double equals 1337. I just made that up literally. I'm going to implement that as an operator next. So the idea is we're going to have equals for unification, and we're going to have or, the double pipe, for disjunction, and double and for conjunction. And because these are logic operators, and because these already exist in Pure, I prefix them with a question mark, meaning logic. Sort of work. So this would mean that we unify Q with 1337, and the implementation for that, first of all, I have to declare a leftwards infix operator with the same precedence as double equals with this, and then I can actually type out the rule for it. So u question mark double equals b. It's now implementation. Now we remember that the goes are functions that take a state, and the state is an s, and an s being a dictionary, and a c being a counter, which is a number. So we declare a lambda function. The backslash is like in Haskell, how you declare a lambda function. And it takes a tuple of s and c. This gets pattern matched out, of course. So it will only respond when called with a tuple of two values, and s and c will bound to the two values. And the implementation for that is it is not matching. We try unify u and v with, we got the dictionary s out of the passing state. So if that fails, what should we return?
So they're returning a string.
Yeah, we are supposed to be returning a string, and if this fails, obviously we should return the empty string, and I define that to be m0. If it succeeds, if we match s, the return from unify is of course a dictionary. So we call that s. What should we return now? A string containing a unit being s and c. Because now we're returning the full state, not just the dictionary.
What is C?
C is the counter in which variables. It starts at 0 and then we try to define what it goes up.
When does it lambda run?
What?
When does it lambda
When we run it later. Essentially, what this operator should be giving us out is a function that we can then call with an initial state from the go. Which I'm going to try and do now.
It's closed over U and V. The way it happens.
It is indeed.
It's
Yes.
closed over and produce a function called later to evaluate.
Yes. This will produce a flowchart, knowing what U and V are. So let's run that. Now let's see first of all what happens if we do something like, so logic variable 0 and typing them out. Or we could go, well, using our function to do it. Question mark double equals version 37. That gives us a closure. And that is a closure that we should be able to call. And we can pass it, did I define empty state? No, I need to define empty state.
Sorry, is that the standard function def impure, or have you done it with a lambda function?
I'm sorry?
Is that the standard function def impure, or have you used the lambda thing to make it clearer for us?
I don't understand the question.
No, it's a function returning a lambda rather than.
Okay.
Yes, this one is this is the function, and this is the result of the function.
Sorry.
And the result of the function will be a lambda function, which we just got down at the closure.
But do you mean that you could have just defined it as a function all the way, just
No, I think you were correct in understanding. I'd misunderstood the first time.
Yeah, after that equals you just start running a function, right?
So shall we try running it up? Actually, try and call that function, see what happens. And I need to define empty state as the default initial state, because I don't want to type empty edge digits, 0 every time. Right. So this is still giving us a closure. Wrap that in parentheses and invoke the result of that to an empty state. This should run it up. Indeed it does. What we get there is logic 0 bound to 337. And that seems to be correct. Let's try the different permutations of that. So something unified with itself returns an empty dictionary, which means it succeeded, but there's no fact that needs to be added. And this returns an empty list, an empty stream. That means it failed. This code had no answers for the empty state.
In for example, R0 should the counter be 1 now? Because 1 0 something?
Yeah. is that we haven't. And that's the next operation I'm going to do. So I essentially been faking that up until now just by typing squiggle bracket 0 or bar 0. But of course, when I do that, I should increment the counter. And this brings us to the next operator, where you define logic variables. And I'm going to make a function called fresh, which takes a function f, and it returns a go. That will be S and C, returns, and we call function f with var of c. C now should be, if it's the empty state, it's going to be 0. And var of c will return logic variable 0. And the function f that we're passing as an argument to call fetch should take one argument, and that argument will be your next logic variable. And we call that.
So when you put empty state there, it just applies the list of empty states that are repeated as 2 arguments, rather than passing empty state in as one after the first one.
Oh, no. The whole tuple gets passed in as one argument.
But that is not there.
Oh, this one.
2 arguments. Right?
Yes, S and C will be 2 arguments, but it's really just one argument being a tuple of S and C. So I pattern match that out.
Yeah.
And yes, so f, it should be a function that takes a logic variable and returns a goal that presumably uses that logic variable. So we call that goal with s and, you guessed it, C++, we increment the counter in the state. So let's see what happens when we do that. So the way we are going to find logic variables now would be to pass in a lambda, which takes an argument q. This is going to be our logic variable, as a called fresh. And then we can do something like q equals, should we go with a shorter number, 5? It's the novelty. That gives us a closure. We call that closure with the empty state. We get variable 0 back to 5. And notice right at the end, the 1 instead of the 0. So now we're actually doing this properly. That's 2 out of 4 operators. We've nearly done, aren't we? Just going to add one function, because I'm sick of typing that. We'll go with G, or G with entity state. So I can go called go on this. And then this is something it's got that Haskell's got as well. The dollar is, instead of wrapping the rest of the line in parentheses, you just go dollar and the rest of the line would essentially be wrapped in parentheses. And it has the same effect. Good. Saves me some typing. Now, next up, disjunction. So it's all very well to be able to say that q equals 5. Now we want to get more interesting than that. We want to say things like q equals 5 and q equals 6 as well. To get really complicated. And to do that we need disjunction. And disjunction, to build that, we will need 2 functions dealing with streams. First of all, we need, because disjunction is essentially the result of all the goes that you are disjuncting. Is that a word? So we will essentially need to run all those goes and then concatenate the streams. So we need a function that takes 2 streams and joins them together. We will call that m plus, because Haskell. M plus takes 2 arguments, by the way. There are 2 streams. If the first one happens to be empty, then obviously the result will be just the second one, because we're concatenating. M plus. If the first one is not empty, we pattern match out the head and the tail. And S2. Then the result would be the head and m plus of the tail and S2. Does that make sense? essentially recursing through the lists here. This will be in a standard implementation of procrastination.
I may have missed a part along the way, so I think it sounds like a stupid question. But in theory, could we pass something that isn't like a list to S2, and then it would like nil?
Yeah.
Okay, so it's not always guaranteed to return.
No.
List.
In Haskell, I expect. I mean, these lists could be heterogeneous. They could. I mean, these are essentially concepts. It could be like a concept, and it might not be a proper list. So anything could come out of this, and S2 could be absolutely everything. And there's no reason it should even be able to come together. Right now, the last element of SS would have to be comes with S2 here, or I should think you get an error about how Pure would deal with that error. I don't know. It could get really weird. But yeah, there's no guarantee that any of these will be actual streams. We have to make sure that that's because it's dynamic typing. Right, and plus. Just quick check to see how it works as expected. Strings being simple lists. 1, 2, 3, 4. Semicolon. 1, 2, 3, 4. Basically. Empty cases. Empty list. 1, 2. Yeah. Short right. Empty list. String through. String through. Great. Oh, well, that was obvious. What if? One plus the 2 comes to string 2. That's fair enough, actually. It's an improper list now, but it still works. Okay. We're going to add one more because we're going to need that for conjunction later. Bind. Bind takes the stream and the goal and applies the goal to each element of the stream. So essentially the monadic bind. If the stream is empty, then M0, empty list. If the stream is not empty, go. And plus the result of running the goal on the head onto the result of binding the tail. Right, so disjunction. And so that was going to be question mark double pipes. Same precedence as pipes. And implementation takes 2 goes, G1, disjunct, G2 equals. And this is a go, so it should be a function that takes S and C. And this is quite simple. Essentially, we take O1 and we run it on S, and we take O2 and we run it on S, and we join them together using M+. G1 S and C, G2 of S and C. Let's test that. So, all go. Choose a logic variable, or crash, Q equals, Q equals 5, disjunct Q equals 6. Fairly straightforward. What should be the result?
Keeping 2 dictionaries.
How many dictionaries?
2.
2 dictionaries. Indeed. One says Q is 5. Logic variable 0 will be Q. And one says Q is 6. Fine. That's exactly what we said. So we're doing good.
But they have the same counters. You simply have both of them the count of 1.
Oh yes, there's only one logic variable. I didn't define 2 logic variables. I defined one to be either 5 or 6. Now let's do infix array. Say precedence as and question mark. Implementation and G2. Much the same, except we bind the result of G1 SNC to G2. So that actually completes µKanren. Let's test that. Now we're saying Q equals 5 and Q equals 6. So what should we expect?
Empty dictionary. Nothing.
Empty. Indeed. Good. That seems to be all in order. Right, that was µKanren. Really something interesting with it. So I showed you the appendo at the start. Let's try and actually get to implementing appendo. First of all, hey. Because I'm not entirely sure we're done, actually. Because suppose we have a rule like this. This should be something I want to call fresh. Alright, with Q. And we say that Q equals 5. Or Q equals 5 of Q. What this should give us if we run it with call goal, call fresh 5s. Should give us an infinite stream of Q equals 5, essentially. So what happens when we try to run that? What do you think? Error. I've done something wrong. Oh yeah, sorry. No, wait a minute. Correct, isn't it? I don't have a typo. Do you see a typo?
But it should show me
Is the-
it's satisfied by the first thing.
Is the recursive call meant to?
Replace that with and probably with confirm.
Let's try and do this. Did I recompile it? Oh, that explains it. Yeah, I did recompile it. So now I'm running it, and what happens is I get a stack fault. Actually, a stack fault. Because I got a stack overflow, because I'm trying to evaluate this quite aggressively and to an infinite depth. So I got a little problem. I can't handle infinite streams, and that's a requirement for µKanren. How would I solve that? By making the list lazy. How would I make it lazy in a language that doesn't support laziness by default? I would wrap it in a lambda function that takes no arguments. Now, this is what perhaps falls apart in as a teaching language for µKanren, because one thing, it doesn't have the facility for defining lambdas which take no arguments. It does, however, have optional laziness. So instead of doing the lambda sum and dot, where I would essentially add tests in n plus and bind to see if S1 might be a function, then I would call the function and keep going and resolving it. Or either return a function that would call the function or something to keep it lazy. Fortunately, pure, and actually let me show you how you do laziness in pure. So suppose you have the value 5. That's the value 5. We can declare that to be lazily evaluated by appending the ampersand. And it's that easy. If we evaluate that, it's going to be a thunk. And if we call that thunk, suppose we actually need it for something, like adding another 5 to it, it will automatically solve that for us. The thunk is essentially a lambda function that takes no arguments. That will only be evaluated when you need it, but you don't have to call it explicitly. It will pure will notice for you that this is a thunk. I need the value of the thunk, so I'm going to run the thunk. And that gives us 10. So we're going to do sort of the same thing here, and this is, it sort of feels like cheating, because in actual paper there's this whole song and dance we're solving lambda functions, but what we need to do,
If you manage the lambda functions, you end up, the return type ends up being a pair of the head of the list and then the procedure.
the tail of the list could be a function. So if you you see a function, you're going to have to call it to resolve it, to essentially do laziness manually. All we need to do is say that this should be a func. And likewise, down here, this should be a func. And one more thing, if we are going to do infinite recursion here, we also need to make this a func. And that gets a little more complicated. Instead of 5 sub q, we can actually have to return a go. That takes S and C, and I'm not going to, just going to keep passing it in, so I'm not going to match it out. And returns a func of 5s of x, call it C. Func. Right.
What is x?
X, I'm an idiot. Q. Is of course what I meant. There we go. Thank you. Because Pure wouldn't have told me that wasn't the type. Just ignore on. So yeah, what was I doing? Call goal, call fresh 5s. What happens now? Now that we've got laziness. Essentially, it's got the first result there. That is the state with a dictionary and a counter. And it's constant to func. So yay, that seems to be a lazy list at least. We'll need to resolve that. We can force it by using the list function, which takes something and makes the list out of it, including a lazy list. Because what happens then is it doesn't return. Because that lazy list is infinite. But we're getting somewhere. We can make another function. Along with call go.
Is that going to run out deep in the
it seems to be doing tape order elimination or something, so it seems to just run forever. At least in my experiments, I haven't run it for more than 10 seconds. I took that as time, but.
But with your implementation of pipes, you don't even need to do this, because you can just like go one level deeper and yeah, you don't need to do this. Maybe it does.
Yeah, actually, what I discovered by accident a couple of hours ago is that given that we thumped the results of calling the go in the second position of 5s, don't actually need to make these lazy. It will still work properly. But I'm not entirely sure why, so I'm not going to elaborate. What I'm going to do is I'm going to implement a pull function, which takes a number n and a go, and it allows us to specify how many results we want from the stream. Take n of although g. So instead of running this forever, we can pull 10 out of this code, and we get 10 states saying that Q is fine. Yeah, that sorts that. Now, there's another requirement in µKanren. In Prolog, this search would exhaust 5s. And if I disjointed it with something that was also infinite, I would never see the results of the second one. That's step first search, essentially. µKanren though requires interleaved search. Meaning, let me just show you what I mean. 6 is a Q, 6, and 6. So that's an infinite list of Q equals 6. And 5 and 6 is call fresh Q takes 5s of Q or 6s of Q. So this is a go, and we can pull, let's do 4 values out of 5s and 6s. That gets us 4 saying Q equals 5. And no mention of the 6s at all. And that will be okay for Prolog, it's not okay for µKanren. So we're going to have to implement interleaved search. How are we going to do that? Hint, because it's an n+. us. This is ridiculously simple. So instead of essentially, when we consing the list together, instead of consing the header of S1 onto the result and passing the tail of S1 onto S2, we just swap them. So that will get the head of S1, the head of S2, second of S1, and so on. And that's interleaved search. That's literally it. Look at this. Now when we pull 4 out of it, first one's 5, second 6, 5, 6, so on. We've got interleaved search. That was easy. Okay. Now the only thing that remains is the actual appendix, because now we actually do have a working with appendix. So I don't think we need these before. However, I've got some cheating to be done here because I don't want to type all this out. It's not really interesting. But I got all these. We're just going to paste over directly and then explain them, and then I'm going to show you the appendix. So what am I adding? I'm adding a macro, fresh, which helps me define body parameters a little more reasonably. I'm going to show you. Got a function 3 sets, which is how to name the function that does laziness for you. You'll remember in the Python I did goal takes S and C and so on, and this does it for you with function. I got essentially these 2 helper functions for my 2 ways of running the program. These are operators, and let me just show you how they work. So instead of pull 1 out of, I need to go now. Pull fresh. Q equals 5 or Q equals 6. Should get us 1 result, Q is 5. Instead of pull 1, I can just go 1 less than question mark on the go, and it. Notice what happens now, by the way. It suddenly becomes much more readable because in addition to running the go, I'm running it through the reify first function, which essentially resolves it all for you and outputs just the value of the first logic variable, which is what we usually want to query with our program. So that's saying that Q being the only logic variable with bound, it says that it has 1 possible value, 5. So
it's like using a cut in prologue.
I'm honestly not sure. I don't think so.
You evaluate so far, and then it drops further solutions. It's like
that cutters. Okay. I don't know.
Yeah, it's
I'm not
completely a
very much
hack.
better.
It's completely a hack.
Yeah, that's my
Essentially, what
impression.
you've
I
done
think that's
is
sort of
get rid of all the searches after you found your first thing.
yeah. That's what I'm doing here. Essentially, I'm just saying, just get the first result from that stream of answers. And I could go on. I could get like 10 results. Of course, there are only 2, 5 and 6. And if I want to run all results, shouldn't be a problem for this stream. I go question mark star for the run star of the original µKanren, which gets all results out of it. If this were the 5's stream, then it would go on forever. Right, so that introduces a bit of syntactic sugar. Another one, and that's, I'm just going to do this one instead. Are we good? Yeah, we're good. Okay. So instead of all the core fresh stuff, I could go, I've used the macro that I just defined, fresh, Q, in, Q, 5, or Q, 6. Oops. What? Is there a syntax error?
Yeah, I think it's because you pressed Control C before.
Yeah.
I just can't remember that you pressed it.
Oh yes,
So now.
I think I sorted that. Yeah. It's a mystery language. Anyway, so that does the same thing as all the call fresh some dogs. So I find that a little more reasonable, don't you? Now, appendo. This one's interesting. So appendo, you recall, takes 3 arguments. It takes the first part of the concat, the second part of the concat, and the result of the concat. And of course, if we feed that with values, that won't, the concatenation values that won't produce the third value, then you would get a failing unification. If you introduce logic variables, you can figure out the possible values that go in that sort. The sorts are left and right and out. So, implementation. First of all, suppose left is empty, the empty list. That makes it a lot easier to write. So if we say that L is the empty list, then R has to be out. Are you with me? Is that a reasonable implementation for the case where N is the empty list? Out must be R. Now the next one gets tricky. So this one, we're going to have to do a bit of cruncing and things here. We have to sort of iterate over the list. So we declare more variables, A and Z, for the car and the coda, just because we already used it. And not even try to explain what's going on there. Essentially, we're saying that A comes onto D, which is L, and A comes onto S, which is out, or out, and lazy, recursive appendo DRS. Right. I'm so glad I have this in my notes, to be honest. Am I going to try and explain it? Essentially, it does the head and the tail thing, and it compares each value of out to what it should be in L and R. And it works, trust me. Let me actually check that it works. So, run a program, fresh, Q, in appendo. What shall we try some? Try on something that shouldn't work. And let's see if it works correctly first. Let's try the boring case that I started out with. What should Q be?
That should be the front of you.
This 1, 2, 3, 4, 5. Let's hope it is. That's a list with a list 1, 2, 3, 4, 5 in it. That means this was the only possible value of Q. So far, so good. What if we toss it nonsense? 1, 2, and Q. Ooh. Oh, pattern match. I guess that makes sense. Because we expect lists here. So empty list Q. Empty list. Fair enough. All right. So Q. 3, 4. 1, 2, 3, 4, 5.
Two in the queue.
One Q in the end.
Oh, yeah. Because that wasn't what I was expecting. I expected an error, but it should be, this is impossible. 3, 4, 5 there should be possible, and Q should be less than 1, 2. Good. Seems that it's working. Now the fancy one. Fresh Q A B. And first of all, we need to say that Q, because we want to know what A and B are, not what Q is. So Q has to be A and B, and appendo of A and B, and 1, 2, 3, 4, 5. Ah! It works. Cool. What happens if we say A, B, C, and put C instead of the list? Doesn't terminate, apparently. Well, save fault, it's stuck over. I wonder though if we could get 10. So, I have no idea what's going to happen now, I just came up with it. I didn't try this in advance. You essentially see everything I've prepared so far, with the append at the end. What's going to happen here? sure?
I've never been playing.
Yeah, apparently you were right. Huh? Yeah. That's a shame. I was hoping it would just generate a lot of lists. Which is probably would just logic higher. Oh well, it was worth a try.
One thing I forgot, probably from the very beginning, how it knows which one
Yeah.
they can see are which logic variables. Which logic variables have numbers, right?
Alright, so how about this? Looking and seeing. Oh, this should be straightforward. I'm asking you to generate all possible lists where. Oh no. No, that's not no. No, that's not right. So what's the other way, right? Or do we have an error? Yeah, where's the other way? Someone actually.
Is that C there an unbound logic variable? Or is
No, it's just a symbol.
Oh yes, it's the symbol. Sorry, I meant to type 1. Yeah, that makes more sense. Well, it's worth a try. Anyway, I have implemented µKanren and I hope that made some sense. Even in the weird, very, very weird language that I just used. Scheme seemed too easy. I suspect most of you can sort of read lists anyway, so I figured I'd try one that is less familiar. Pure is actually a very cool language. Even if you still have no idea how to do µKanren,
So,
you want to know how to go at Pure.
what kind of things would you use Pure for?
I am entirely unsure, to be honest. I just picked it because it looked like fun and I wanted to learn it.
So I've seen typed term writing,
Yeah.
and I can't imagine, and they're really super strict. Any type error, right, nothing works, your problem, fix it, and then we'll
Yes.
evaluate something. So the idea of even, I would never have imagined that this could exist.
Well, I sort of came to it from the other direction. I only just realised that you could do this type as well, and I'd really like to try that trick. But yeah, no, this is how you normally go about any assembly writing language without the types.
So I've seen hardware people, not software, not it hadn't really occurred to me that the software developers would be interested in it. I've seen people that design concurrent hardware, people that are trying to worry about sort of semiconductor correctness, dealing with turbulent, but not really people worried about efficient software.
Yeah. So the use cases for Pure seems to be, I mean, looking at the available libraries, it seems that it's being used for mathematics
Okay.
as sort of a, not a replacement for things like MATLAB or that sort of thing, I would think, but as sort of an accessory to it. And there's lots of sound processing findings for some reason, and some OpenGL, and I think that's about it. So, I mean, it's got a tiny user base. It seems to be a very solid compiler and an extremely solid idea. Though, would I want to write something larger than µKanren is? I'm not sure. Because it takes me like an hour to even figure out what an error is.
Yeah.
For example,
So
fixing it.
I don't really understand how it could ever be fast.
It seems to be. I mean, it might just be the magic of LLVM, which is the
Okay.
music.
Yeah.
I
Okay.
don't know.
So the FFI side of it. Okay.
Yeah. But it seems to be, I mean, you might have noticed that if I just type something I haven't done before, don't know, this might be quicker, yeah. But at least after restarting it, it sort of takes a while to warm up. Then after that it goes very quickly. And it seems to be a very efficiently, a language that compiles to something quite efficient. I don't know, honestly I learned it last weekend. So I don't know.
Why do programmers have that use case anyway?
Usually
just run for their own.
It tells you a lot, but if you I kind of like to know what people use it for. It kind of gives me some direction.
I can tell you what I plan to maybe use it for at least. Because, okay, so this is science fiction, and please don't repeat it outside this room. to turn off the camera that will be boring. So, essentially, I really like Emacs, but it's sort of showing its age, and I thought maybe I should have a stab at building an editor that retains the idea of Emacs, but gets rid of Emacs Lisp and other things from the previous century. And I was looking for a scripting language to replace Emacs Lisp. And I think type languages are completely out. I would just go for Idris or whatever else is cool like that. And I was looking for a decent untyped scripting language that could replace Emacs Lisp in an environment that essentially requires a lot of mutability by design and by necessity, probably. And it seems to be an interesting candidate. So I think my next project might be to actually try and, because my editor needs to run on my computer, which is a Chromebook, I have to write it in JavaScript. So I'm going to try and make a JavaScript interpreter for Pure next. See how that goes. So that's not me using Pure to build something, but that's me building Pure on something else. So.
Why do you say that an editor by definition or by design needs to lots of usability?
I don't know if an editor does, but Emacs certainly does. And I'm trying to sort of stick with the core ideas of Emacs because that's worked for the past 30 years at least. So it's probably onto something, but Emacs Lisp I'm not so sure about. Lisp 2 and everything, those people are crazy. I don't know, it's an experiment. Maybe, probably I'm never going to finish it, but it'll be fun. It's a nice little language at least playing around with, definitely. And now you've got a logic programming for it as well, so what's not enough?
So what's the difference, coming back to logic programming, so what's the difference between relational programming, the interpreter that you just implemented, and logic programming? Because unification algorithm for Perl looks exactly this way.
Yes. I'm going to venture, and correct me, Dan Freeman, if I'm wrong, if you ever watched this, that they're about the same thing.
So like different names for the same
Logic programming is a vaguer term, I think. Relational programming has a very specific meaning, which is what you just saw, and I think right on.
Cool. If there's no more questions, we'll wind up there. Thanks very much, Bodil.